At this point in the course, we have already learned one way of describing the motion of an object moving in two dimensions. What we do is we imagine that as the object moves along, it carries two flashlights. One flashlight is a blue flashlight, which points directly at the x-axis, making a spot of blue light, which tracks the horizontal motion of the object. The other is a red flashlight, which points directly at the y-axis, making a spot of red light, which tracks the motion of the object along the y-axis. We can say that the velocity of the blue spot is v sub x, and the velocity of the red spot is v sub y. So that's one way of thinking about the motion of this object. Here's another way of thinking about the motion of the object. What we do is we introduce something called a velocity vector. The velocity vector is denoted v vector like that. The velocity vector points in a direction tangent to the path followed by the object. So coming to the figure, if this object here is moving like so, we would draw the velocity vector tangent to the path in the direction that the object was moving in, like this. The other thing you need to know about the velocity vector is that the magnitude of the velocity vector is equal to the speed of the object. So here I've given you a complete definition of the velocity vector. The direction of the velocity vector is tangent to the object's path, pointing in the direction of motion, and the magnitude of the velocity vector is the speed of the object. So it looks like I have given you two completely separate ways of thinking about the motion of an object moving in two dimensions. We have this flashlight idea, which gives us Vx and Vy as separate velocities along the two coordinate axes. And then we also have this velocity vector. So what is the connection between them? The connection is that Vx and Vy are the components of the velocity vector. So let's say we would take that velocity vector there and place the velocity vector with its tail at the origin. So I'm just going to take the velocity vector and shift it so that the tail lands at the origin, and I'm drawing a clean figure over here. If I then take the velocity vector and project onto the x-axis, then this component, v sub x, is the same as the velocity of that blue spot we were talking about before. And if I take the velocity vector and project onto the y-axis, then what I get here is the y component of the velocity vector, and this is exactly the same as the velocity of the red spot as we were discussing earlier. I'm going to do a quick example to illustrate the point. So this example is actually going to use the final velocity vector from the previous problem I showed you. Let's say we have x and y axes, and I'm going to put a velocity vector in here with given components. Let's say here's our velocity vector. Okay. So let's say we project onto the x direction, and we find here that the x component of the velocity is 30 meters per second. Let's say we project onto the y-axis and find that the y component of the velocity is minus 39.6 meters per second. So based on this information, let's say that we try to find the speed and direction of motion of this object. So first, the speed. The speed is the magnitude of the velocity vector, and we can calculate the magnitude of any vector using the Pythagorean theorem. So magnitude of the velocity vector would be Vx squared plus Vy squared, square root. So let's substitute. So we have Vx 30.0 meters per second, quantity squared, plus Vy minus 39.6 meters per second, quantity squared, square root. And this gives us 49.7 meters per second. Now we'd like to find the direction of motion. So you can see that the direction of motion would be some angle below the x-axis. But what would that angle be? Well, let's call this theta. Okay, and we can use our usual ideas about right triangles to find the theta. I'm going to put in a right triangle here. And to avoid the awkwardness about that minus sign there, I'm just going to think of this as a geometric triangle where all the sides are positive by definition. I would then say that tangent theta equals the opposite side. So the opposite side, if I'm forcing it to be positive, would be minus Vy. And then we have the adjacent side, Vx. So we have theta equals inverse tangent minus Vy over Vx. Now substituting, minus Vy would be 39.6 meters per second. Vx, 30 meters per second. I get theta equals 52.8 degrees. So a full description of the velocity vector would be to say that the object is moving at 49.7 meters per second in a direction 52.8 degrees below the horizontal. In the next video, we're going to do an example problem where I give you the velocity vector as part of the given information.